Hi there, welcome back. This is Professor Hank, and in this video we are going to continue our discussion on binary search tree algorithms. Specifically, we're going to look at an algorithm that can be used to free all of the memory that is used by the tree. Recall that with a binary search tree and other data structures that they rely on dynamically allocated memory to create the nodes that are going to be storing the data that you want to preserve within the tree, right? So because of that, we have to have an algorithm that's going to go through and remove each of those dynamically allocated nodes, right? So it's going to have three main points. It's going to free all memory used by the structure. We have to make sure that once all of the nodes are deleted, that root is left in a valid state, which is to say that the root pointer isn't left pointing at an invalid memory location. In other words, we have to make sure root gets set back to null. We're going to use recursion in this algorithm, and we're going to use post-order traversal. Post-order traversal or processing, okay? And it's important to keep in mind that for this algorithm, right, if you were to implement this as a function or a method, that you're going to pass by reference. Okay, so let's go ahead and get started. Okay, so here's what the algorithm looks like. We're going to accept a node's memory address by reference. That's what the ampersand in front of the R is representing. First thing we're going to do is we're going to check for null, right? We can't delete a node if there's no node, right? If we have an invalid memory address, if we have null as memory address, no node to delete, right? So that's going to be our base case. That's when the recursion is going to stop. But if we get past that because we have a memory address for a node, well then what we're going to do is we're going to delete recursively, or we're going to clear recursively our left child, and then we're going to recursively clear our right child, and then we'll go ahead and delete ourselves, right? So the children get deleted first. Now to ensure that the root node gets set back to null, we'll go ahead and overwrite the memory address that we were passed with null. Let's go ahead and take a look at how this would work. Okay, so here we go. We're going to start off by passing the memory address of the root node to our clear algorithm. Memory address is stored inside of a root pointer, right? Each one of these boxes right here is going to represent one of the nodes, and we're back to using zeros to represent null, okay? All right, so first thing that's going to happen is that we're going to have multiple instances of this algorithm running at the same time, right? Because it's a recursive algorithm. Okay, so what I'll do to represent that is I will denote the reference parameter of each instance of the algorithm with R sub 0, sub 1, sub 2, for example. Okay, so the first instance is going to begin executing and is going to have the memory address of that very first node, right? And I'll label that node node 1, and then I'll label the left child 2, and I'll label the right child 3. Okay, so first instance, call it R sub 0, has the memory address of node 1. Okay, and what's going to happen is that its base case is going to be checked. Is R set to null? No, because we've got the memory address of node 1, right? So we get past the base case. Now we recursively are going to clear the left child node, right? So that's going to cause a second instance of this algorithm to start running. We'll call that R1. It's going to be past the memory address of the left child. So that instance is going to begin running. R0 has to wait until R1's done before it can continue. So we have two instances of this algorithm running at the same time. So R1 checks its base case. Is its parameter null? No, it's got the memory address of node 2. So then it goes and attempts to recursively clear R1's left child, right? So it's given the memory address of its left child. Well, it doesn't have a left child, so what happens, right? The R2 instance hits its base case, its parameter is null, so that guy terminates right now, okay? And because of that, we then return back up to R1, and then R1 has its next instruction execute, which was to recursively clear its right child, right, which causes another instance of the algorithm to begin. That instance is given null as an argument, so it hits its base case and it terminates. Okay, so then we're back up to R1. R1 has now gotten to its delete instruction, so causes node 2 to be deleted. Okay, and then the last thing that it does is it sets its parent pointer to null. Okay, and then it leaves memory. It's done. Okay, so then once that's finished, we return back up to R0. R0 is taking care of its left child. Now it's going to go to its right child. And a similar thing is going to happen. Okay, so we're going to get another instance of this algorithm running, this time giving the memory address of node 3, the right child of the root node. Okay, so no base case, not null, node 3 exists. So then the next instruction in the algorithm is to check or attempt to recursively clear the left child. That instance is past null, so it's done. We return back up to R4. R4 then tries to recursively clear its right child. Its right child is past null, so it's instantly done. Okay, so now we can return back to R4. R4 has cleared both of its children. Now it can delete itself. Okay, and once it's deleted itself, then it sets the pointer that it was passed to it to null. Okay, now once that's done, we return all the way back up to R0. That instance has now cleared both of its children, and so it's now free to delete itself. Okay, and then after doing that, the last instruction it performs is to set the pointer that was given to it to null, right? So that's how it works in general. We delete the children first, and we make sure that root gets set to null when we're done. Okay, so one more example, one that's a little more interesting. We're going to go ahead and invoke our clear algorithm by passing the memory address of the root node to the algorithm. So we pass node A's memory address to the root algorithm. So this is what's going to happen. Okay, so the order in which this stuff's going to get deleted is going to be the following, right? We're going to attempt, first thing we're going to do is we're going to check to see if, remember the algorithm's going to first check for null. Well, A's exists, so the memory address passed to the algorithm not null. So then what do? We take care of the left child, right? Then we recursively repeat that. Okay, again, not null, so take care of the left child. Okay, we go to D. So we go from A to B to D. Once we get to D, D has no children, right? So we try to clear the left child, try to clear the right child, nothing happens. And so then we're free to go ahead and delete that child, right? And then as part of the last thing that the algorithm does, or the last thing that algorithm does, is it sets the pointer back to null, right? Now once that happens, we return back to the node from whence we came, and then we take care of the right child, right? So the right child, in this case, no children, right? Both cases, nothing happens there, so then we're free to go ahead and delete that node. And then once that happens, the last thing that clear does is set the pointer to null, right? Once that's happened, we return back from whence we came. Okay, we're back up to the B node now. Now B has cleared both of its children, so it's free to be deleted now as well, right? Once that happens, it leaves memory, and the last thing that clear does is set that pointer to null. Okay, once that happens, we return back from whence we came, back to node A. Node A is taking care of its left child, now it needs to take care of its right child. Okay, so we're at node C. Node C has to take care of its left child. Well, no node there, so it goes right back, returns right back from where we came. So node C's left child's taken care of, then we try to take care of its right child. Recursively, we're going to make another attempt. So node F, going to first take care of its left child recursively. Get to node G. Node G tries to take care of its left child, doesn't have one, so we go right back where we came from. Tries to take care of its right child, doesn't have one, so we go right back from where we came from. So now that both children are taken care of, we can now delete the parent, right? So the last thing that clear does is sets that pointer to null, right? So now we go back to the parent. Parent then takes care of its right child, doesn't have one, so we go right back to the parent. Now that both children are taken care of, we can delete the parent node. Parent node's gone, and the pointer set to null. Okay, once that happens, we return back up to C. Okay, now node C, both of its children are taken care of, so now node C can delete itself. Okay, now that node C has been deleted, the last thing clear does is set the pointer back to null. Okay, now that that's done, we return back from whence we came, back up to the root node, node A. Node A's children are both taken care of. So now, node A is free to delete itself. Last thing that clear does, sets the pointer that was handed back to null. So we got a tree that's been removed from memory, and we've got a tree that is in a valid state because root pointer is set back to null. Okay, so let's go ahead and do some analysis. The running time of this particular algorithm is going to be big O of n. Why? Well, the reason for that is because we're going to have to visit and delete each node one by one, which means that the number of operations that we're going to have to perform is going to directly correspond to the number of nodes that exists. We're going to have, say, 6 nodes in the list, therefore we have to have 6 deletions. Therefore, this implies big O of n. We're going to have an algorithm that runs in linear time, right? And so why is that? Well, what's going to happen is we have to visit node D, delete it. We have to visit node B, delete it. We have to visit node E, delete it. We have to visit node F, delete it. We have to visit node C, delete it. We have to visit node A, delete it. So the more nodes that there are, the more deletions we have to have, okay? Okay, so let's summarize. In conclusion, what we have accomplished with this algorithm, or details that we've discussed with this algorithm anyway, is that we freed all the memory that was used by our binary search tree. We made sure that the root pointer was left set to null. We used recursion in this solution. We made sure that we passed by reference to make sure that the root pointer at the end did in fact get updated. We required the use of post-order processing to make this happen. And we saw that we had a running time that was big O of n because we had to visit each individual node and delete each individual node one by one. Okay, so that's going to bring this video to a close. Thanks for watching. If you found the video useful, please consider giving the video a thumbs up. And if you thought the video sucked, well, you have the option to give that video a thumbs down as well. If you're interested in seeing more content like this, there's the subscribe button you can hit as well. And as usual, if you're a student of mine and have further questions, please feel free to shoot me an email or stop by my office hours. Thanks for watching, and we'll see you next time.